Alright, let's do another example where we're working with a family of sets. So we're still going to have F be a family of sets, and we're going to let A be an arbitrary element of F. In this example, we're going to show that the intersection of F is a subset of A. So it's kind of similar to what we did, but just a little bit different. Again, let's start with a little concrete example. Just for the heck of it, I'm going to let F be the family of sets with just two elements this time. One of the elements of F is the set whose elements are 1, 2, A, B, C. And the other element of F is a set whose elements are 1, 2, 3, B, E. Okay? If I was to compute the intersection of F, that means to compute the intersection of all elements of F. So I would take the first set, and I'd intersect it with the second set, and I'd intersect it with the third if there was, and a fourth, and a fifth, and a sixth, and so on. In this case, though, there's only two elements of F, so I only have to intersect two sets. When I look at this, when I intersect sets, I find the common elements. And by looking at this, I can see that the only common elements between these two sets are the elements 1, 2, and B. So the intersection of F is the set 1, 2, B. What I can see now is that for any x that I grab out of intersection of F, so whether that is 1, or whether that's 2, or whether that's B, I can find a set A in F that contains it, and they all contain it. So any x that I grab in this intersection implies that x is an A. For example, what if I grabbed the element 2? So 2 is in intersection F. Both sets in F have 2 in it. The first set, 1, 2, ABC, has 2 in it. The second set, 1, 2, 3, BE, has 2 in it. So for this specific x that I grabbed in intersection F, it's definitely in A for any arbitrary A. Or what if I grabbed B? Same thing happens. For picking B, which is an element of intersection F, B is in the first set, 1, 2, ABC, and it's in the second set, 1, 2, 3, BE. So no matter what x I grab in this intersection, x is in A. And this is what it means for these things to be a subset, right? Okay, so that's a concrete example showing how we think this is going to work out. I'm always going to have intersection F be a subset of A, and this concrete example resulted in that. It's not a proof, but it gives us a little picture of what we think is going on. So now for the real proof. So let's do our kind of transformation method again. Let's start off with our assumptions. F is a family of sets in A and F. And what we're trying to show is that intersection of F is a subset of A. So that's what I start with. What we're going to do is we're going to transform what we want to show, or our goal, one step at a time. So I rewrote the givens, and now I'm going to transform intersection F subset of A into something a little different. What does it mean for a set to be a subset of another? Well, it means for all elements in the first set, this implies those elements are in the second set. So I just wrote down a logically equivalent statement. For all x, x in intersection F implies x in A. Okay, so I've transformed it one little step. And this line gives me a clue now. I'm trying to show something and show it's true for all x. So when you see that for all x, that's your clue to transform your given statement or your assumption to tack on one extra thing. That extra thing is going to be let x be in intersection F. So now we can rewrite our goal here, what we want to show. I've let x be an arbitrary element of intersection F. So this boils our goal down to x needs to be in A. So now this is really easy to show. From the given here, we know that x is in intersection F. So that means that x has to be in every element of F. That's what it means to be in intersection F. Guess what? A is an element of F. So since x is in every element of intersection F, x has to be in A. And then we're done. We just showed that x being an element of intersection F implies x is an element of A, which is the definition of a subset, and that is our formal proof.